Welcome back. Today we're going to talk about section 6.4, the difference in means. And there are really three parts to this section 6.4. We're going to have to do a little bit of work on what the underlying distribution is for the difference in the sample means. That'll be the first part. Then we're going to show how to take the theory and develop confidence intervals. And then we're going to show how to take the theory and conduct hypothesis tests. So I will put these each in a separate video lecture so that you can return to them as you need to. But our first task today is to talk about the underlying distribution. Now, before we get too into that, let's remind ourselves of why we would study a difference in means. So let's take a look at a problem that we could have solved back in chapters 3 and 4, where we just work with bootstrap confidence intervals for a difference in means. Let's look at a typical problem to put this into context. So let's let mu sub m and mu sub f denote the mean number of hours of exercise per week for male and female college students respectively. So those are parameters that exist within the population of male college students and female college students. All right, now we want to know something about the difference between those exercise hours, about the parameters themselves. So what do? A random sample of 50 college students consisting of 20 males and 30 females were asked how many hours a week they exercise. Now we're going to load StatKey. We're going to go to confidence interval for a difference in means and load the file exercise hours male female. In using the sample data, we're going to create a 95% bootstrap confidence interval for mu m minus mu f. So we're going to use the data itself to bootstrap a set of differences in the sample means, and we'll be able to find a 95% confidence interval using that technique. So here we are, confidence interval for difference in means. We're going to load the file exercise hours male and female. So there it is. Here's the data that we collected from those 50 students, 20 males and 30 females. We noticed that within the samples, the males are exercising 12.4 hours a week, and the females are exercising 9.4 hours a week. That is a difference of 3 in the samples. But as we know, when we go from sample to sample, the difference between these X bars is going to vary. And so what is bootstrapping doing? It's allowing us to see how that variation plays out if we were to repeat this experiment over and over and over again with 20 males and 30 females being selected each time. So let's let the bootstrapping begin here. We're going to generate several thousand samples. And so StatKey is showing us through simulation what the variety of samples would produce in terms of the difference in their sample means. Okay, now to get the confidence interval, we just have to carve out the middle 95% of these dots, and that StatKey is just going to do that by counting dots. So we just go to two-tail. It defaults to the middle 95%. And so this tells us that our confidence interval is going to extend from about negative 1.517 to 7.592. So there's our 95% confidence interval for the difference in those population parameters, mu sub m minus mu sub f. Okay, now we have to think about what would it look like if we were to do this by theory, right? How would we develop a confidence interval just using theory? Well, we've been practicing this technique for a while in a variety of other circumstances, and so we would expect that if we wanted to understand the difference between mu sub m and mu sub f, it's going to be composed of some parts. The first part is going to be, what is the data telling us already about the difference in the sample means? That's the best estimate. So we would start with our best estimate. That's what the sample is announcing to us about the difference in the sample means. But then we know, because these samples, each time I collect a different sample, I'm going to get a different set of sample means to work with. We know that we have to add on a margin of error in our calculation. We know that our best estimate is just an estimate for this true difference. And so we add on a margin of error. And as we've come to expect, that margin of error is itself composed of two pieces. One is the standard error. That would be, you could think of that as the standard error in that dot plot that we're creating. And the other one is the multiplier, which is composed of two parts, right? The multiplier carries with it the amount of confidence, the confidence level that we want to attain. So that's part of the multiplier. But the multiplier also carries with it some knowledge of the underlying distribution that's driving this. We've already seen two different options for this. We've seen the standard normal distribution, and we've also seen the t-distribution. And so now the question is, we're going to see this same form replicated. The question is, what is it going to look like for this particular kind of, in this particular context? So let's see if we can answer these questions. What would be our best estimate for the true difference in the means? Well, it would be that the difference in the sample means taken in exactly the same order. That's our best estimate. What is the standard error? We'll construct a theoretical formula that will tell us how to get that standard error right out of the samples. And do we use a z or a t cutoff for the multiplier? It turns out this is more like a single mean in this case. It's going to be a t distribution. So we're back to a t distribution, helping us form that multiplier or that cutoff value. All right, we'll get to that in just a second. All right. So as we read this theorem, this is kind of the theorem that's driving everything we're doing in this section. We have to remember that when we sample from two different populations and form an x1 bar and an x2 bar, every time we draw samples, x1 bar and x2 bar are going to be changing. And so the difference between them, x1 bar minus x2 bar, is itself changing from sample to sample. So we have to think of x1 bar minus x2 bar as following a distribution of possible values. And what this theorem is trying to tell us is, what would that underlying distribution or set of dots, if you will, what kind of shape would it have? So let's read the theorem with that in mind. When choosing random samples of size n1 and n2 from populations with means mu1 and mu2 respectively, the distribution of the differences in the two sample means, x1 bar minus x2 bar, let's think of that as the shape of the dot plot, is centered at the difference in population means mu1 and mu2 and has standard error estimated by the formula. So the standard error of the difference is composed of the standard error of the two underlying pieces. And so you get this Pythagorean relationship once again. So the standard error of the difference is equal to the square root of the sum of the squares of the underlying standard errors. So the one from population 1 and the one from population 2. Now, we'll break this out and look at a formula for this, but just remember that this is exactly the same thing we saw when we worked with differences in proportions. We have that same Pythagorean kind of identity here. All right. The standardized differences in sample means follows a t-distribution with degrees of freedom approximately equal to the smaller of n1 minus 1 and n2 minus 1. That is, we could think of our degrees of freedom formula as the minimum of n1 minus 1 and n2 minus 1. So this is just saying we're always going to have two numbers to compare, and we always choose the smaller of the two to get our degrees of freedom. So this is a little reminiscent of working with differences in proportions, and it's a little bit reminiscent of working with just a single mean. So we're seeing a little bit of a flavor of both of those here mixed in. Now, underneath this line here, I'm acknowledging that all of this is predicated on either working with large samples, that's n1 and n2 are both greater than or equal to 30, or we're working with samples themselves that appear to be drawn from a normal distribution. So we would want to know that in the case of small sample sizes, that both of our pieces of sample data are looking approximately normally distributed. So we'd want them to be symmetric-ish and looking kind of normally distributed. Okay, so we'll talk about that as we work on some specific examples. All right. One way to think about this result, and this will be helpful as we especially think about hypothesis testing, is that if I were to take x1 bar minus x2 bar, subtract the center of the dot plot, so to speak, mu1 minus mu2, and divide by the standard error of the difference, this should conform to a t-distribution curve. with degrees of freedom specified by N1 and N2. So that's one way of thinking about this result, that this critical ratio that we could form here would conform to a t distribution. All right, so that's another way of thinking about this. Now, what I want to do is spend a little bit of time thinking about what the standard error of that difference looks like. So let's break this out in this particular case, because we saw that the standard error of the difference looks one way when we are working with a difference in proportions. It's going to look a slightly different way when we're looking at a difference in means. So let's take a look at that. So recall that if we just concentrate on population 1, the standard error of x1 bar is S1 over the square root of N1. Likewise, the standard error of just x2 bar by itself would be S2 divided by the square root of N2. So if we use our Pythagorean idea, if we want to get the standard error of the difference, we have to square this one, and add them together, and then take the square root. So we can see that the standard error of the difference is going to be S1 squared over N1 plus S2 squared over N2, all inside of a square root. So that's a fairly simple formula to work with for the standard error of the difference. We just have to remember, I think there's a couple of places here where I think people could go wrong, and that's to forget to square the S1 and S2, and then also to take the square root here at the end. So just pay a lot of attention when you come to this. All right, now this is basically what we need to do to work with the distribution. And what I want to do is close this first short video lecture by working a couple of examples, a couple of problems to show us how we can just get comfortable with just the distribution part here. So let's take a look at a couple of closing problems here from this first part. So a psychologist is interested in studying mu1 minus mu2, the difference in means of a measurement within two populations. All right. Random samples were drawn from each population, and the results are shown in the table below. So we can see here that from population 1, a sample of size 120 was drawn. Within that population, whatever measurement that was being studied had an average value of 96 and a standard deviation of 10. Okay? Within population 2, there was a sample of size 93. That same measurement within population 2 had an average value of 90 and a standard deviation of 14. Okay, so using this information, find the standard error of the difference for the differences in the sample means. So we're going to want to find the standard error of essentially x1 bar minus x2 bar. All right, then a follow-up. Do the standardized differences in the sample means follow a t distribution? If yes, specify the number of degrees of freedom of the associated t distribution. And if you remember what that second question is getting at, it's asking, do we have large samples? If yes, then we're done. If the samples are small, can we infer something from the samples themselves to convince us that we can go forward and assert the t distribution? So let's take a look at that problem at the whiteboard, and then we'll come back and look at one more problem. All right, welcome to the whiteboard. Let's work this first problem together. We've got the information. I've taken the information from the slide and transported it here so we can take a look at it together. Our goal here is to first calculate the standard error of the difference in the means, and all we have to do is assemble some of this information appropriately. So the standard error for the difference is just this kind of Pythagorean theorem idea. We take the standard error for population 1, which is going to be squared, so it's going to be 10 squared over 120, and then we add to that the standard error for population 2 squared, so it'll be 14 squared over 93. So that's the basic calculation. Now let's take a look at that. I'm going to do 10 squared. I'm going to divide that by 120. I'm going to store that. And I'm going to do 14 squared divided by 93, and I'm going to add to that what I had in memory. So this sum here is on the order of 2.94. I have to take the square root of that. I end up with a standard error of 1.715, and that'll be good enough for our purposes. Okay, so that fulfills part one of the problem. All we had to do was just get used to using our standard error form and pulling the information out of this table. Now, the second part of the question asks us, do the standardized differences in sample means follow a t-distribution? And this is really just a question of, are the kind of conditions in place? Are we allowed to use the t-distribution? Are the conditions that underlie the theory in place? Now remember, there's a couple of things that we would check. The first thing that's easy to check is we would just look at the sample sizes, and what we're seeing is the samples are of size 120 from population 1 and 93 from population 2, and those are both in excess of 30, which is the kind of the cutoff. And so since both of those are bigger than 30, we would say yes, the conditions are satisfied. Now, once the conditions are satisfied, we would like to know what is the number of degrees of freedom for the associated t-distribution. And remember, all you have to do is compare these two and say, all right, I need the minimum of 120 minus 1, so that's 119, or 93 minus 1, and that's 92. So I just have to find which is the smaller of the two, and that's going to determine the number of degrees of freedom. So our number of degrees of freedom is simply going to be 92 in this case. All right, and that's all we have to do to fulfill the obligations of this problem. So let's move on to the next problem. Welcome back. We've got one more problem from this first part of section 6.4 that I want us to look at. And in this problem, we're just trying to get comfortable with the degrees of freedom concept and how to do a calculation with the corresponding t-distribution. So we have to, in this case, find the proportion in a t-distribution less than negative 2.1 if the samples have sizes n1 equals 20 and n2 equals 35. Now, this is asking us to imagine that there's the t-distribution curve that's been associated with this difference in means x1 bar minus x2 bar. And we want to know how much of that curve lies to the left of negative 2.1. Now, the thing that we have to pull out of this is we have to understand, based on these two sample sizes, what would be the appropriate number of degrees of freedom to use for that t-distribution curve. So as I'm continuing to talk here, we're going to go to the whiteboard and work this out, but you can begin to ask yourself, based on a sample of size 20 from population 1 and a sample of size 35 from population 2, ask yourself, what number of degrees of freedom would I use in the associated t-curve, and how much area, therefore, lies to the left of negative 2.1. Okay, now, we're going to assume the samples are random samples from distributions that are reasonably normally distributed, and that a t-statistic will be used for inference about the difference in sample means. So state the degrees of freedom used and find this proportion. Okay, so let's go to the whiteboard and we'll work this problem out, and hopefully by the time that we're done working that problem, we'll have a pretty good handle on how the distribution of the difference in the sample means behaves. All right, that will bring a close to part one of section 6.4. And so I will join you on the other side then for another video where we explore just the confidence interval concept for a difference in means. All right, let's go to the whiteboard and check this one out. Okay, welcome back to the whiteboard. We're going to work this problem, and there's a little bit you have to kind of understand about the way this problem is phrased. We have to imagine that we were working with some samples, one from a population of size 20 and the other from a population of size 35, and we're trying to apply this t-distribution theory to these samples. Now, we're being asked to calculate, in a sense, what would amount to a p-value. Let me draw the curve for you. So here's our t-distribution curve. We're being asked to calculate this area that sits to the left of 2.1, under the t-curve that would be associated with this underlying distribution. So that's kind of the background. Now, the thing we'd always ask ourselves first is, are the conditions in place to apply the theory? And if you read back into the problem, it says, assume the samples are random samples from distributions that are reasonably normally distributed. Now, we would be concerned about that because in this case, one of the samples, this one here, is considered small. It's less than 30. So we would be concerned about trying to apply our theory in this case. And so this is a sincere question. Are the conditions in place? And the way the problem is phrased, the conditions are in place. We can reasonably assume that these underlying distributions that the data is coming from are normally distributed. Okay. Now, all that's left to do is we have to figure out what is the t-curve that underlies this. And really, that's just a question about the degrees of freedom. So when we do our degrees of freedom calculation in this case, all we have to do is compare two things, right? We want to look at the minimum of this sample size minus 1 and this sample size minus 1. And when you compare those two, you'll see that the minimum is 19. So this is going to be a t-distribution with 19 degrees of freedom. So you'd go into StatKey, you'd fire up your t-distribution, you'd plug in 19 degrees of freedom, it would ask you that right away. You type in negative 2.1 on the x-axis, and you want to figure out how much area, this is in a sense like a p-value calculation, how much area sits to the left of negative 2.1. And I just had it work that out. This ends up being 0.025, or equivalently, we would say 2.5%. So there's our final answer. We have 2.5% of the total area under the t-curve sitting to the left of negative 2.1. And that's all we have to do to finish off this problem. So this closes off the first part of these notes on section 6.4. We're going to pick up with another video lecture that covers building confidence intervals. So I'll meet you in that next video lecture. All right, bye-bye.